The universe has a way of reminding us just how little we truly know. It operates on scales of time and distance that dwarf human comprehension. But every now and then, it sends a messenger. We are currently tracking such a messenger. Its designation is 3I divided by Atlas. And in approximately 12 days, this colossal object, weighing an estimated 33 billion tons, will make its closest approach to our Sunday. It is traveling at a velocity that defies easy explanation, nearly 80 times faster than a bullet fired from a high-powered rifle. As a theoretical physicist, moments like these are what I live for. They are the ultimate test of our understanding. The cosmos throws a challenge at us, a puzzle box made of ice and rock and deep time, and it dares us to solve it. But I must confess, this particular object has captured my complete attention. There's a confluence of factors here: the trajectory, the timing of its arrival, the fundamental physics at play, that all converge to create a brief, critical window. A window in which we could witness a breathtaking natural spectacle, or something else entirely, something engineered, something that our science is not yet prepared to comprehend. And here is the most unsettling part. During that precise, critical moment, we will be completely blind. Right now, 3I divided by Atlas is performing a maneuver that is, from a celestial mechanics perspective, profoundly unlikely. Imagine our solar system as a vast, spinning disk with all the planets orbiting in a relatively flat plane called the ecliptic. Most interstellar debris, true cosmic shrapnel from distant stellar events, dives in from chaotic, random angles. But not Atlas. This object is skimming along the very edge of that ecliptic plane, tilted at a mere 5 degrees. To a physicist who studies orbital dynamics, this is the equivalent of throwing a dart from across a room at a spinning globe and having it land, not just on a specific city, but on a single designated street within that city. Our first two interstellar visitors, the enigmatic Oumuamua and the more conventional 2I divided by Borisov, followed paths that were much more predictable. They sliced through the solar system at high, steep inclinations. Atlas, however, is hugging the planetary traffic lanes. And in orbital mechanics, geometry is not just a detail, it is destiny. Mark your calendars. On October 29th, at approximately 11:55 Universal Time, 3I divided by Atlas will reach perihelion, its closest point to the Sunday. It'll be just inside the orbit of Mars, at a distance of about 1.36 astronomical units. Its velocity will peak at that moment, reaching a staggering 68 kilometers per second. And it is precisely at this point of maximum velocity that one of the most powerful and elegant concepts in astronautics comes into play: the Oberth effect. The fundamental principle of rocket science is this: if you want to achieve the maximum possible change in your trajectory for a given amount of fuel, you must fire your engines when you are moving at your fastest. To put it simply, if you intended to dramatically alter your cosmic destiny, perihelion is the moment you would choose to act. Now, could a natural comet execute such a maneuver? The answer is no, not in any meaningful way. Comets do experience what we call non-gravitational accelerations. As they heat up, jets of gas and dust erupt from their surface, giving them tiny, unpredictable nudges. But these are mere whispers and puffs. To break free from a hyperbolic escape trajectory and enter a stable orbit would require an enormous change in velocity, tens of kilometers per second. This would necessitate a precise, powerful, retrograde burn executed perfectly at perihelion. If such an event were to occur, the evidence in the data would be unmistakable. We would observe a sudden, step-like drop in its outbound velocity, a change so dramatic that no model of natural cometary activity could possibly account for it. But here is the crux of the problem. During the very moments when such a maneuver would be most efficient and logical, humanity will be looking away. The rules governing our most powerful observatories are not mere suggestions. They are inviolable laws etched into their hardware and software. When an object on the sky approaches too close to the sun, our ground-based telescopes must cease observations. Our eyes in space face the same limitations. The Hubble and James Webb Space Telescopes are physically prohibited from pointing anywhere near the sunday. Other spacecraft, like the Parker Solar Probe and Solar Orbiter, are designed to stare at the sun, but they are optimized to study plasma and magnetic fields, not to track faint off-axis comets. The collective result of these safety protocols is an observational blackout centered perfectly on Atlas's perihelion. Whatever happens in that period of darkness, whether it's a spectacular natural fragmentation, a mysterious and sudden fade, or, in the most exotic and unsettling scenario, a controlled, intelligent course correction, we will not witness it in real time. So, what do we know as we head into this blackout? Enough to label 3I divided by Atlas as interesting in the most profound scientific sense of the word. Our preliminary data, gathered before the object disappears into the solar glare, has already revealed a host of anomalies. Photometry and spectra show a coma that is unusually rich in carbon dioxide. Polarimetry, which measures the orientation of light waves, indicates an extreme negative polarization at certain angles. This hints at a surface composed of fluffy, fractal dust, very different from the dense, silicate-dominated grains we see in comets from our own solar system. Some research teams have even reported detecting emissions of nickel without a corresponding signature for iron, the chemical pairing so strange that it is still under intense scrutiny. Dynamically, the object is just as puzzling. Despite having a large and active coma, it has shown little to no non-gravitational acceleration. This leaves us with two possibilities. Either the nucleus is far more massive and dense than its brightness suggests, or the venting of gas from its surface is happening with astonishing symmetry, perfectly canceling out its own thrust. Speaking of its mass, early estimates placed it in the tens of billions of tons. Yet, when Atlas passed by the planet Mars on October 3rd, our navigation teams did not detect the expected gravitational tug. This discrepancy opens the door to a range of alternative theories. Perhaps its albedo is fooling us. Perhaps the brightness is being inflated by a vast cloud of dust. Or perhaps we are looking at something with a highly porous or even a hollow shell-like structure. Now, allow me to put on my futurist hat for a moment, because the geometry of this encounter almost compels us to ask the question, what if this is not just a rock? If 3I divided by Atlas were a vehicle, a probe, or a delivery system, perihelion is precisely where you would expect it to act. The Oberth maneuver is not just a theoretical curiosity, it is the cornerstone of efficient interstellar travel. Instead of disintegrating into a random spray of cometary fragments, you would look for evidence of order. You would search for discrete objects moving on coordinated trajectories. You would look for fragments that appear to steer rather than drift aimlessly. Physics is elegant in this regard. It provides us with falsifiable signatures. If we do not observe these specific signals, the more extraordinary hypothesis collapses under the weight of the evidence. But if we do see them, then our textbooks will require an urgent and profound update. So here is the post-blackout checklist I would give to my graduate students. The series of tests we must run the moment 3I divided by Atlas reemerges. First, astrometry. We must nail down its outbound trajectory with extreme precision. A sudden change in velocity of even a few kilometers per second will be unmissable. Second, deep imaging. We must hunt for multiple fragments and analyze their paths. Nature sprays debris randomly. Intelligence organizes. Third, polarimetry and spectroscopy. We must repeat the pre-blackout measurements and compare the results. Look for sudden, discontinuous changes in the composition of the dust and gas. If the numbers tell a story of gravity and nothing more, we will have learned a marvelous new lesson about the natural diversity of the galaxy. But if the numbers do not add up, then we will begin a very different kind of conversation. There is a wider lesson to be learned here, regardless of the outcome. In less than a decade, we have been visited by 3 confirmed interstellar objects. Our current fleet of telescopes is magnificent at observing the sun and distant galaxies, but it is not optimized for chasing faint, fast-moving objects that pass within a few degrees of the solar disk. The universe is sending us these incredible high-speed laboratories on flyby trajectories. We must be ready to use them. Let me close with the anchors, the facts we can state without speculation. October 29th, perihelion, a speed peaking near 68 kilometers per second. A retrograde orbit just 5 degrees off the ecliptic. This is a one-time visitor. Early November. Recovery. We will begin to see it again in the dawn sky. December 19th, Earth's closest approach at a safe distance of nearly 1.88 astronomical units. What we know is that its pre-perihelion behavior was dominated by carbon dioxide activity, that it displayed extreme negative polarization, and that it has so far shown minimal non-gravitational acceleration. 12 days, that is the drumbeat. If Atlas is a natural wanderer, we will witness how pristine interstellar ice and dust react to the intense furnace of our Sunday. If it is something more, the laws of physics will leave behind fingerprints that we cannot possibly miss. Either way, the final verdict will belong to the data that begins to roll in after the glare subsides. I tell my students every semester that in science, the greatest danger is not in being wrong. It is in being certain before you have the measurement. The universe is about to write the next chapter in this story. Behind the blinding light of our Sunday, our job is both simple and profoundly difficult: to watch, to measure, and to keep an open mind.